session with David Dritschel from University of St. Andrew, and he will talk about dynamics and statistics of point vortices on a sphere.
Thank you very much. So first of all, I'd like to thank Elena and Milton for the invitation. It's a great pleasure, as always, coming to Brazil and Rio in particular. I apologize in advance to the cameraman because I tend to move around a lot, so you're going to have a challenge to follow me. The work is in collaboration with Marcello Lucia and Drew Poje at City University of New York, Staten Island. We had conceived this idea about 3 years ago when I was visiting New York for a colloquium where I met a variety of people interested in various aspects of flows, two-dimensional flows, and we had this idea to investigate further the statistical mechanics and dynamics of flows on spherical surfaces. As we'll find out, it's a fairly old subject, but the statistical problem of point vortices seems to be new. So, if this works, yes, okay. So I'd like to begin slowly by giving some motivation for why we're doing this work in the first place. At least people doing more classical fluids have been interested in trying to understand why self-organization, probably the greatest question in fluid mechanics, fundamental questions is why do we get order out of chaos, if you like, in fluids? It's a question that's bothered many people, and there's still an open question to figure out exactly what the correct interpretation or way to go now in this subject is. I'll give you a couple of ideas that people have been pursuing. The first, they both actually appeared at the same time in the mid-1900s. The first is the so-called dual cascade of two-dimensional turbulence. I'll be focusing only on two-dimensional flows essentially at infinite Reynolds number. Two-dimensional flows are regular flows. I'm thinking about either bounded vorticity in the case of the dual cascade, which I'm talking about here, or with point vortices, singular vortices that we've been seeing already during the last few days. They're quite different, as we'll find out. So the alternative explanation started with Lars Onsager, who we've already heard twice about, and you'll hear about him again in the same paper. A third conjecture made there about the statistics of point vortices in planar surfaces, in particular arbitrary domains on a plane. After giving that introduction, which is mainly a review of some history and contrasting different approaches, I'd like to talk briefly about the setup of a new experiment that we conceived of a few years ago of looking at point vortex dynamics on a sphere and to try to explain why this is a nice thing to do. Then look at the statistical properties to address Onsager's conjecture. Then consider dynamical evolution of large numbers of point vortices, the question of ergodicity, which has still not been proven for the system, and the idea of so-called cascades to try to link point vortex dynamics to traditional views of two-dimensional turbulence. I'd like to maybe interject at this point that for a long time there have been two parallel communities running side by side, hardly interacting, and this is an attempt to somehow bridge this together. And the two theories represent very different ways of thinking about what we regard as the same problem. We'll revisit and try to bring everything back together in the third section, where we'll talk about the dual cascade again and compare continuous and discrete vorticity, and then discuss disorder versus order and a few conclusions. So, of course, the Great Red Spot, fantastic structure, Earth-size vortex has been there for hundreds of years, if not longer. Why? Why do we get a structure like this? There are thousands of papers on this subject already. Many papers already on planetary atmospheres trying to understand the structure of the flows there. The Earth itself has an interesting structure. The fact that the weather is not just a random sea like molecules in this room is interesting. And it's fortunate because weather forecasting would be pretty much impossible, or it would be very boring because nothing would ever change. The fact that we have differences, we have fronts, we have vortices, is something inherent in the underlying equations that govern fluid motion. And this is what people have been trying to seek an explanation in the fluid dynamics. We see it in computer simulations. Vortices appear naturally in flows spontaneously, and you get other things like jets. So this is something we see time and time again. Now, since probably the early 70s with Formberg and then McWilliams later and many other papers since, people have been looking at decaying two-dimensional turbulence. What you find is that starting from a random state of some form, and people have tried almost anything you can imagine, after early times, the vortices start emerging out of this, condensing, and at the end, well, not really an end state, but later in time, you find that only a few large vortices remain. There's this sense that there's an inverse cascade. There's a growth of scale in the problem, starting from relatively small scales to larger scales. The observant person might say, well, the scale of this vortex doesn't look much bigger than the one there. In fact, that's true. Many people have missed this point. The actual thing that's growing here is not so much the vorticity structures, but actually the circulation patterns around the vortices. This is an indication of the energy growth at large scales that we'll come to in a moment. But this is called the inverse cascade. It goes back to a paper by Fjortoft in 1953, who basically pointed out that in two-dimensional turbulence, at least in the inviscid case, both energy and a quantity called entropy, which is just the mean square vorticity, are conserved quantities in the flow. If you look at their spectral densities using Z or Z, depending what pronunciation you like for this symbol, if you take the entropy here, this is the magnitude of the wave number and the Fourier amplitude squared of the vorticity, the entropy is known by Fjortoft's argument to, if you start from a narrow-banded structure in wave number space, this is a typical initial condition, like the one I just showed you a moment ago, then it's observed that the entropy typically spreads mainly to large wave numbers, which means small scales, and the energy, this kinetic energy K, the kinetic energy density spreads to low wave numbers or large scales. This is an exact result if the distribution of the initial conditions is a delta function here, then you have to have the spread as long as there are nonlinear interactions in the problem. So nonlinearity is what's causing the spreading to take place, which makes it difficult. So the inverse cascade of energy, which you hear all the time in two-dimensional turbulence, very different from three-dimensional turbulence. It's unique to two-dimensional turbulence. This inverse cascade is basically this dual cascade constraint that you have to conserve both entropy and energy, and you get this kind of spreading that takes place. This is an important picture which I'll ask you to remember, but I'll bring it back up again because it's relevant to the difference between how point vortices behave and finite vorticity. So we've already heard about Onsager several times, so this is the third occurrence of the reference to the same paper, where in his discussion of point vortices, he proposed an alternative explanation a few years earlier than Fjortoft, arguing that what's really happening is kind of like a Boltzmann gas, that you think of point vortices swarming around and somehow collectively organizing into these structures like the Great Red Spot. And he thought that maybe some kind of statistical average of microcanonical ensembles, that means very large numbers of point vortices swimming around in space, would produce macroscopic mean states like the red spot, and explain the so-called inverse cascade, or why we have structure in geophysical fluid dynamics or in fluid dynamics, two-dimensional fluid dynamics. So he exploited the two-dimensional point vortex model of Kirchhoff that was known around for many years already, known to be a finite Hamiltonian system for a finite number of vortices, and he took a general domain D. Essentially, he followed closely Boltzmann and assumed that the vortex dynamics, like molecular dynamics, is ergodic, so that the time averages that you might perform over a single realization of an experiment ultimately will equal the ensemble averages over equal probable states. So it's a definition of entropy, or of ergodicity, which is not proven, Many people have tried to check this, and there have been arguments or results both ways about this, but I think we'll see this question addressed later on, so I won't let the cat out of the bag just yet. But that's important for the argument that ergodicity applies. So what did Onsager see about point vortices that are different from a gas? So we know that a gas typically doesn't, like at room temperature, doesn't organize into anything but an opaque background, boring mixture, which is fortunate because we can see through it and we're not suddenly knocked over by a big coherent structure, typically. So what he observed is that if you take, say, red vortices or, say, positive ones, the blue would be negative, and you just throw them at random in a domain D, and you do this countless times, over and over and over. Each time you do that, there's some kind of interaction energy, which I'll define in a moment, which you can calculate, that essentially gives you the kinetic energy of the flow minus an infinite contribution of each vortex that you subtract away. So what's left over is so-called excess energy, which you'll see Onsager uses in his argument. It's a well-known conserved quantity. It's the Hamiltonian of the problem. Essentially, you compute this Hamiltonian, or the energy, for each realization thrown at random. And when you do that, you basically then calculate the density of states, which is proportional to or is related to the entropy of the system. So the entropy is defined by the log of essentially the density of states, or the PDF, the probability of finding, or the probability density function of energy, or interaction energy. So you can think of P of E dE as the probability of finding a random microstate, one of these realizations of energy between E and E plus dE. Now, the key thing that Onsager demonstrated was that for the point vortex system, it must be that the entropy has a maximum somewhere in the domain. He showed that at large energies, the entropy decreases, and at small energies, the energy also decreases. In fact, he also showed that there's no bound on the energy. The energy can go to plus infinity and minus infinity. And I'll explain why that happens. So there's a maximum occurring at finite energy for some particular energy. And that's funny because this doesn't occur for molecules. If you look at Boltzmann's theory of gases, well, of course, you have also not just positions, you have momenta that, yes? The number of particles is fixed here, yes. So in the Boltzmann theory, you also have to worry about the momenta and positions, and you find that the entropy then always increases in that system. So you don't have the situation of the entropy always increasing with the total energy of the system. And therefore, you can define an inverse temperature in the classical thermodynamical sense as the rate of change of entropy with respect to the energy. And this is the inverse temperature, beta, which is often used in the theory. This is always positive for Boltzmann's theory. In this case, you see that because we have a maximum in entropy, the entropy starts decreasing. We have this region at high energy where the so-called temperature, if you can even call it that, is a negative quantity. So it's a weird kind of system. So that's why Onsager got very interested, because this is very different from what molecules do. So what are the consequences of that? So he noticed that at the very high energies, where the inverse temperature is negative, these high energies must be associated with close like-signed vortices. Here's the expression for the interaction energy between a pair of vortices. So gamma I, gamma J are just the strengths or circulations of the two vortices, positive or constants. They can be positive or negative. If they're both the same sign, then this is a positive number. Then it's negative. But the log of a small distance is negative, so it becomes positive. So you notice that basically when xi and xj are very close to each other, the positions are close to each other, that will contribute a positive interaction energy. And that can be arbitrarily large. And likewise, if gamma I and gamma j are opposite sign, you can have arbitrarily negative energy, and this corresponds to low energies. These are so-called positive temperatures. So then he went on to conjecture then that based on this, that if you observe a very high energy system at so-called negative temperatures, it must mean that there are clusters. So he says vortices of the same sign will tend to cluster, preferably the strongest ones. So as to use up the excess energy, this is this energy I've been talking about, interaction energy, at the least possible cost in terms of degrees of freedom. And then he says the weaker vortices, free to roam practically at random, will yield rather erratic and disorganized contributions to the flow. That's about all he says about the statistical mechanics of point vortices. He stops there, and then basically leaves it up to the community to figure out what he said. So this is what people have been arguing about for the last 60, 70 years. And there are at least, well, my count of over 100 papers that are well known on this problem, probably more than that right now. But after that, Joyce and Montgomery, sorry, let's go back. So Montgomery and Joyce in 1974, then many others since have been trying to figure out what was said by this, doing experiments, looking at whether this made sense, doing actually numerical experiments to find out whether you got clustering. Okay, and the question that I would like to ask here, and basically underpins much of the work that's been done, is it a statement about the dynamics? Does the vortex dynamics do something to find or to self-organize? Is Onsager saying something about vortex dynamics, or does he say something about just the statistical properties of vortices thrown at random in a domain? So, to be more clear, does any initial configuration of vortices at high enough energy evolve into a coherent macro state like the Great Red Spot? Okay? You'd like to think that, and I think many people have viewed Onsager's conjecture as saying something about the emergence of coherent structures in two-dimensional turbulence. So you'd like to think that if you're at high enough energies, you will evolve into something like a Great Red Spot. This interpretation goes back, and there's other papers earlier than this, even by Buehler, Yatsuyanagi in 2005, and Essler recently in 2013. And so the real question is, does it explain the formation of coherent structures or vortices in two-dimensional turbulence? Well, first of all, there's some statements in Onsager's conjecture that we need to think about. Does Onsager's argument require a finite asymmetric domain? Why would you think that that's important? Well, it turns out that then when there's no symmetry in your domain, there's only one conserved quantity, and it's just energy. So you only have one conserved quantity for the whole dynamics. So you can sensibly think about a PDF of an energy. If you have a circularly symmetric domain, then you have to worry about angular momentum. Or if you have a channel, you have to worry about linear momentum. So there are other things you have to worry about. So we may wonder about whether these other symmetries cause trouble. Then the question is, do we need to have a mix of strong and weak vortices, as Onsager suggests? That maybe if you have big, strong vortices, you can use up the excess energy with the least constant degrees of freedom. This is what he says. So Buehler was arguing that maybe that might be important. He explored that possibility. Yet, if you read the fundamental argument of Onsager simply noticed that close like-sign vortices contribute a very high energy to the interaction energy. And close opposite sign vortices do the opposite, with just contributing a very large negative energy. So it would make sense that all Onsager's argument requires is that the energy just needs to be sufficiently high, and you'll get clustering. You'll get like-sign vortices to join together. So we're going to basically try to pursue this argument, thinking about the problem from a much simpler point of view than what we think anybody's done so far before, by considering the simplest bounded and boundaryless domain, which is the surface of a unit sphere. So this is the motivation for using a sphere. It's isotropic. Okay? So it has a nice property. It's an isotropic surface. And we can just throw vortices at random. There are many other nice properties, which is that the vortex dynamics is very simple. First of all, the Laplace operator restricted to the surface is, you have Euler's equation, just as on a plane. The Hamiltonian is exactly the same. It's a log of essentially the distance squared. Here, this is the distance squared over 4, but you can take log of distance squared, you get whatever, 2 log, whatever it is. Okay, it's the usual log of distance between vortices, interaction energy. This is the Hamiltonian for the system. And then the equations of motion you can derive from the Hamiltonian are simply given by dx dt is equal to a sum over, excluding the self-interactions, of a cross product divided by 1 minus the dot product. So simple equations, which is convenient for numerical calculation. So you can do calculations of the dynamics easily, and for calculating things like ensemble mean energies, you can use this expression here relatively simply. So this is what we've done here. So the kappa J or I here is just the so-called strength. This is just the normalized circulation. All right, so now, as I said, when you put symmetry, then you start acquiring other conserved quantities. So, for instance, the sphere has a vector angular impulse, which is defined by sum over J of all vortices, kappa J xj. This is a conserved quantity. Here we're going to focus on states deliberately with zero angular impulse to sensibly address the possible emergence of a large-scale order. I say that because you can show that if I is non-zero, then the whole configuration has a mean rotation about the vector I. And so you can argue that how can you address the emergence of large-scale order when the whole flow is rotating at the largest possible scale? So we're going to try to exclude the largest scales in the flow by looking for states that have strictly zero angular impulse. And then what's left over is just the interaction energy. And if you calculate the entropy from the log of the probability distribution, then has the structure which I've already shown, has a maximum, single maximum, and the inverse temperature goes through zero at a particular critical energy, and then for large energies it's negative. So we'll be then sampling this to find out what happens. Okay, so what we did to start with is we said, okay, let's consider a binary gas. So this, to make things simpler, we take n vortices, half of which have circulation 1 over root n, and the other half have circulations minus 1 over root n. And it turns out this convenient 1 over root n scaling ensures that as n goes to infinity, all the statistical properties of the system converge. So we get a convergent PDF, convergent entropy curve, etc. It turns out that by sampling from n equals 2 to 2000, by n equals 200, you get a convergent PDF, and basically the curves converge on the line you see here. So we're going to pick 200 vortices in what follows and generate large ensembles of a certain number of vortices, these 200 vortices. So what we've done is that here's the whole PDF shown here, or the entropy, so log of the PDF. And in each of these bands, 1 through 9, there's 2 lines here, and this gives you the width over which we look for states. So in each of these, so if we take band 1, there's a small range of energies that we're looking for states that have that range of energy. And when we find one, we just add that to the bin or to the number of states in range 1. So we're going to generate altogether 10 to the 4 states in each of these bands so that we can look at their ensemble properties. And notice that down here, the first 4 bands actually correspond to positive temperature, because beta turns out to be positive here, and the upper bands correspond to negative temperature. So the states that might be associated with the formation of coherent structures of Onsog are way out here at high energy, so we'll be looking at that. Yes? That's right. And so what we did in principle, what we did is we set a calculation running for days. We basically said, just throw down vortices at random, and then we calculate the energy. If the energy falls in any of these gaps here, we just throw it away. And when we find one that falls into one of these gaps, we keep it and put it in that band. And we just keep doing that. And after about 10 days of computing on a machine, you finally can fill that up to the 4 states. Kappa is just the circulation divided by 2 pi. Okay? N is the number of vortices. All right, so then we're going to now characterize the ensembles. Look how they vary with energy, or inverse temperature, if you like, in 2 different ways. The first way, we're going to look at what people in traditional 2-dimensional turbulence, not the point vortex community, but people doing 2-dimensional turbulence, have always done from the early days. They've looked at energy spectra. They look at inverse cascades or cascades of using energy spectra. And so what we do is we calculate the stream function. You can calculate the stream function at any point x, say on a latitude-longitude grid, from the known positions of the vortices at any given time. In fact, here for the ensembles, they're just fixed numbers. And then we can calculate the kinetic energy spectrum in the usual way, expanding everything in terms of spherical harmonics and sticking into a black box, and out comes the spectrum. So that gives you then a typical spectrum. And we can then generate an ensemble average kinetic energy spectrum associated with each energy. And then another interesting measure, which is complementary to the two, the other one, is to look at the PDF of normalized pairwise interaction energies. So this Q, this term right here is just the interaction energy between two vortices, kappa I, kappa j times the log of distance squared over 4. And n basically is a normalization that means that this product here is either plus or minus 1. So when Q is positive, it means that you have close like sign vortices. And when Q is negative, it means you have close opposite sign vortices. So it's a way of basically checking whether a given ensemble has more dipoles or opposite sign vortices that are close by, or more binaries, which are like sign vortices close by. And we can check that by subtracting what you get from a random placement of vortices on a sphere, which is a known form. So the residual basically tells you the surplus of binaries or dipoles you might have in the system. And this is what we get. So if we look at these are purely statistics, so we haven't done any dynamics yet. If we look at all the ranges, so this is the traditional two-dimensional turbulence sort of picture of a kinetic energy spectrum. Log of kinetic energy, log 10 versus log 10 of the wave number here. You get the expected k to the minus 1 scaling for all ranges here. This is a singular spectrum, corresponds to the fact that the kinetic energy is formally infinite. We're just calculating the spectrum anywhere. So if we calculate the kinetic energy over the whole system, it will actually be infinite, but it still allows you, it's still sensible to address the energy content at low wave numbers or at large scales. And that's where things differ. So in the high energy range here with negative temperature, we find that there's a surplus of kinetic energy. There's a lot more energy at low wave numbers. That means the low modes in the system, the low spherical harmonics, are full of energy. They're very excited here by this placement. And then, on the other hand, the low energy cases, which have positive temperature, are depleted. So that you notice they have very low energies here. In fact, there's a tendency to fall off as a k to 1 spectrum at very low energies. The complementary view over here in terms of residual interaction energy PDF shows the picture I showed before. I don't know if you can see the curves that well, but I'll try to point them out. Curve 1 here corresponds to the lowest energy. The lowest energy is highest in the range where Q is very negative. That corresponds to close dipoles, opposite sign vortices. So there's a surplus of very close dipolar vortices, and there's a deficit for that curve of close positive vortices. So it's exactly what you expect. And if we go to the other extreme, high energy, which is the curve 9 here, curve 9 at very negative Q has a deficit of opposite sign vortices that are close by and a surplus of like sign vortices that are close by. So it's exactly what Onsager was expecting, and this is consistent. No dynamics. I'll come to dynamics in a minute. Well, this is the consequence of our view. If I wanted to stop my talk here, this is all that Onsager said. Okay, this is the consequence of applying Onsager to the sphere. This is all you get. There's no dynamics.
No, I thought it was. So how did you pick your vortices?
Randomly chose them across the surface.
But then you picked out the ones that you randomly chose them uniformly across the surface, and then you picked out the ones that had a certain energy.
Exactly. That's all. So I basically distinguished 9 different ranges that are different energies. And the first thing that surprised us is that there is a continuous variation of all the properties that you see here with the energy band you take.
You didn't use the Gibbs. Onsager used the Gibbs ensemble. You didn't use that. Or have you somehow used that?
It's effectively equivalent here. We've chosen completely random states here to... Yeah, it's... So the first take-home message here is that there's nothing dramatic happening as you go from positive temperature states at low energy to negative temperature states at high energy. There's a continuous variation of the kinetic energy spectrum. There are continuous variations of all these properties here as well. So nothing catastrophic happens as you go into the so-called negative temperature regime. Okay, maybe one would have expected that. But let's continue. Now about dynamics. So what we did was we said, okay, well, let's just take 100 or so states from each of these 9 energy ranges. So we basically had 10,000 of them at hand. We chose a random 100 or so of them, and we evolved them for some large time, which is about 70 or so so-called eddy turnaround times, which you can estimate based on mean vortex separation and typical circulation values. And then you can do ensemble average and time averages of the various statistics that I was talking about, kinetic energy spectra, and the probability of interaction. And we find that there's no dynamical evolution at all. The statistics are identical. You could not see a difference on the lines. Okay, you might say, oh, that's not surprising. It does tell you something about ergodicity. At least it's evidence that the flow is ergodic. Okay? No statistical evolution occurs. So the dynamics, the vortex dynamics are consistent with the statistical properties. They don't change them at all. Okay, but that's a fairly weak result still. Let's go further. What about atypical initial states? Well, you know, if we go back again, forgetting point vortices and Onsager, and go back to what people have been doing since Fjortoft, they've been saying, well, we like to start from this. We start with a high wave number initial state, narrowly peaked, like Fjortoft was thinking, and we let it go, and we start seeing all these vortices emerge from it, and they get to larger and larger scale. That's the classic inverse. That's what we're trying to understand. That's what I'd like to understand. I don't care about the point vortex macro state necessary unless it can explain this. Okay? So the question is, well, so they do this. Why do they do this? Because, well, first of all, let me point out that the kinetic energy at low wave number, for people that are really paying attention here, they'll start seeing something wrong already. The kinetic energy at low wave number in all these studies is strongly depleted. Eventually, it's almost zero. Because they take a narrow band of kinetic energy at a high wave number, and there's almost nothing at low wave numbers at all. And that's what gives you this sort of honeycombed pattern here, which then rapidly does this, and you get an inverse cascade taking place. Energy starts building at low wave numbers. Okay, this is done because it gives room for an inverse kinetic energy cascade, which people expect by Fjortoft's argument, and indeed it happens every time. And we get the emergence of coherent vortices. So the question is, can this occur in the point vortex dynamics? So in order to test this, the first thing we did is we started from a dipole gas, which are plus minus pairs, separated by some mean vortex separation over root 2. And we created an ensemble of some 111 cases with the energy lying in the lowest energy range, which has, again, for people paying attention, positive temperature. All right, so the people that are paying attention, we're in the wrong regime. We're looking at positive temperature, trying to explain how Onsager's self-organization could take place. It can't. You think, well, how can we explain what we're seeing here, this inverse kinetic energy cascade to large scales, starting from positive temperature when Onsager says that it's all disorder there. This is in the regime like molecules where the entropy is increasing. At positive temperature, you expect disorder in the system. And it's exactly this disordered state that's producing the inverse energy cascade. And this is what happens. So here's the dynamics now. Time t equals 0, this is what you get from ensemble averaging 111 states. This is the kinetic energy spectrum of 111 states, t equals 0. By time 48, that's about 1 eddy turnaround time. The ensemble average spectrum evolves to a state which is almost identical to the curve everywhere except for the larger scales. And by the end, you can't see the difference between the average and the microcanonical mean. So all that happens is that the point vortices run around and they eventually lock on to the typical state for that energy according to Onsager. So it's a relaxation of the flow to this. It's an inverse cascade because there's depleted energy at low wave numbers, and now there's more. So it's an inverse cascade. Inverse cascade, like classical two-dimensional turbulence, is happening for positive temperature states. It shouldn't be. And you can see here, too, that, and this addresses the question of the interpretation of entropy. at t equals 0, we have this big spike. This spike here in this probability of interaction corresponds to a large number of dipoles placed at some distance apart here. So this corresponds to the very large number of dipoles. And then the rest is just sort of random noise. By time 4-8, you can hardly see the difference between the final state, the macrocanonical mean or microcanonical mean and the final state. These curves very rapidly converge together. What happens is that the interaction energy spreads rapidly by the dipoles being separated and becoming random over the sphere very quickly. And this spread of energy is a definition of a growth of entropy in the system. So it's almost like we're having two gases that are suddenly released, put together, and you get the maximum entropy state very quickly. Yes? That's right.
If you look at the simulations of the point vortex model, you see a similar sort of irreversibility.
We'll see that if you... I will get to it. Okay. I will address exactly that in my third section of the talk, but that's a very good point. Yeah. Okay, so I've already said this. There is a cascade, but it occurs for the wrong side for positive temperature states. And that all the statistics converge rapidly. And it seems that the cascade occurs, but only just what is needed to relax the ensemble mean random state. Now, for something very strange, you get a forward cascade. Never seen before in two-dimensional turbulence. People don't do this kind of stuff. But you can actually arrange by picking a atypical high-energy state. And what we do here is we actually project on the lowest permissible spherical harmonic. So we put a lot of energy in mode 2, which is this one right here, and then deplete it afterwards. And what happens is that's t equals 0. Shortly thereafter, it rapidly converges to you can't see any difference between the curves. They converge together to the microcanonical mean state, ensemble mean state that would be predicted by Onsager's theory. So there is now a forward cascade for an atypical state in this case. So oddly again, a forward cascade occurs for negative temperature states, exactly opposite to what you might think Onsager's been saying. And what the sum of these two things means that all states relax to the microcanonical mean for any given interaction energy you start with. So you give me an energy, you choose your favorite set of point vortices, put them anywhere on the sphere. You can put them all in the same point, maybe with a small perturbation. And I guarantee if you calculate that energy, and I could have a spectrum or whatever, it would converge to that. And it would converge to it very rapidly. This is what we find time and time again. And we've done other experiments with quadrupoles that are very close together, which are even more depleted at low energies. And every time we have the same result occurring. And you could say that this is very powerful evidence for ergodicity. It's not a proof of it, but by golly, everything wants to go to the ensemble mean. This is basically verification that ergodicity probably applies here. As a picture of the stream function, you can't see this as well. You have to have probably good eyes for seeing these things. The low energy states, this is what we started with t equals. So this is an atypical low energy state. And this is supposed to look like it's smaller scale than these two pictures over here, which is the final state for this forward evolution and a typical state from the same energy. So this is supposed to look like has larger scales, which I think you can see the blue and red patches are bigger. So there's a growth of scale. It's an inverse cascade. And then the forward cascade case, here we start, you see this is a whole sphere view of rolled out, if you like. Here is the lowest spherical harmonic, okay, the pattern, with some perturbations. And then it breaks up into something that is a mixture of the lowest spherical harmonic and a few others. So this is actually a forward cascade to smaller scales. And this is the end state, and this is a typical state from the ensemble. So the point is that these two things look similar. These two things look similar. The states either evolve forward or backwards to get to that state. Okay. So Onsager's negative temperature states have been often associated with the inverse kinetic energy cascade two-dimensional turbulence. And the controversial statement here, which I think we've demonstrated at least for point vortices or on the sphere, is that this interpretation is misleading and plainly incorrect. It does not apply for at least point vortices on a sphere. I don't think that would generally apply in other cases. The atypical, strongly positive energy states at negative temperature result in a forward cascade, whereas the atypical, strongly negative energy states at positive temperature result in an inverse cascade. And this is just the reverse of what one would expect if Onsager's negative temperature states had anything to do with the inverse cascade. So what instead we observe is a strong relaxation of any state to the microcanonical ensemble mean state of the same energy. And all the evolution has in mind is just to relax to that mean state. And it's independent of the system's temperature. Whatever temperature you start with, it just goes to the state of that particular energy. Ergodic hypothesis seems to be correct for point vortices on the sphere. So Onsager's theory in this context is no more than a statement of relaxation. And I would say it's wrong to interpret negative temperatures with clustering and the formation of large scales in two-dimensional turbulence. So for a lot of people that work in this area, this is a very dangerous statement. I probably have things being thrown at me at this point. But this is what we seem to find. We don't see anything more than the simple relaxation taking place. And it goes contrary to what you'd expect based on what people have been saying about Onsager. So I'm going back to the same picture as before of the Joule cascade picture. So back to Fjordhoff in 53, we've seen this idea that entropy must go to small scales, energy goes to large scales if they start at, say, a single scale times 0. And we know from Fjordhoff that the inverse cascade goes hand in hand with a direct entropy cascade. You can't have one without the other. Entropy can't just sit there while energy goes to large scales. They have to go in opposite directions always. And that's because both are conserved. They have a different spectral type of shape. And they have to do this. But there's no analog of entropy in point vortices. Entropy is the square of vorticity integrated over the surface. You can't square a delta function or delta distribution. There's no definition of entropy. So that's missing already. And you could argue that point vortices, well, they can't deform and they can't fragment, unlike continuous vortices. And this is exactly where this entropy cascade is coming from. It's from the deformation of continuous vorticity that allows the entropy cascade to take place. So if point vortices have no sense of entropy, how can they get the energy cascade correct? So to address this, we're going to basically try to test whether this idea of vortex deformation is essential. So we started instead with a situation which might look very simple here. These are actually point vortices. There's so many of them, something like 35,000 of them. I think this is the record calculation for at least a calculation which has been very careful to conserve energy. So I didn't say this, but we've been extremely careful to conserve energy to at least 8 digits of accuracy in these calculations. This is thought to be essential. We didn't want to do anything less than this. So it takes time. You have to have adaptive time stepping methods and maybe have to go back and correct the solution until you get conservation. So we want to conserve energy. These kinds of calculations using this many vortices have to be done on a large cray with thousands of processors for days on end. You think it's a waste of time to do this. They're very costly calculations. But we wanted to see whether the point vortices could do things that finite vorticity could do. Okay, how much can they reproduce? So we basically chose, it turns out that on a sphere, spherical triangles very easily set up. So you can basically set the point vortices into arrays of triangles and make a hexagon. And hexagons are kind of nice because if you think about the dynamics, they're all going to splay out and form sort of dipoles. You'll see that in the next moment, shortly. Well, all right, so that's the point vortices. It looks like the same image, maybe slightly different. We're doing an equivalent calculation using so-called vortex patches. We've heard this from Stefanella earlier. So this is based on using a contour dynamics approach where you basically represent, you actually have to follow only the boundaries of vorticity of each of these triangles. And for this kind of problem, it's a much more efficient calculation. It can be done in a few hours versus on a single processor versus many days on thousands of processors. So we're going to use basically a numerical method, which I'm not going to describe, but basically it's solving an approximation to the Euler equations at extremely high resolutions. Probably this is the highest resolution simulation done in spherical geometry ever. And so you'll see, and if I could had the time and I could blow up the images, you could see the detail endlessly at scales that are well beyond what you can see here. So we're starting from what we think is the closest approximation to the same state. And after a short time, about 1 eddy turnaround time, which we can calculate based on the vorticity here, we basically match the effective vorticity in the two calculations. You see that they're not that dissimilar. The point vortices and the vortex patches are doing the same thing. The same dipolar structures are forming here. You can find similar things everywhere. What you might notice is that the fine details that you're picking up here, these fine filaments that are forming little tadpole tails that are forming behind the dipoles, you don't see them. You see broken up structures. This is the first evidence that the point vortices are, even with 35,000 vortices that, it takes weeks of computing, a single processor would take something like a year of computing for this. Already it's breaking down at a very short time, just 1 turnaround time. And by 10 turnaround times, it starts looking like, how can you compare the two calculations? You can still see lots of clumps here in the point vortices. And you can maybe imagine that might be related to this one here, but it takes imagination at this point. And what you're finding in the vortex patches, in the Euler equations, you're finding that large areas are starting to open up of well-mixed, very fine-scale filaments. This is the entropy cascade going to small scales. And it's allowing for the formation of these coherent vortices, these clumps that are very clearly defined, holding together, unlike what you find in the point vortices. And if you go further, it gets worse for the point vortices. This becomes more and more homogeneous. What's happening, of course, it turns out to be a state at very strongly negative energies or positive temperatures, so it's not surprising that it's disorganizing. But the point is that we started from a state which does lead to a typical evolution of two-dimensional turbulence, and we get something that doesn't look at all like it in the point vortices. If we look at energy spectra, which don't come out very well, I think you can maybe barely see them, the point vortices and the uniform patches initially look similar. The point vortices have a very shallow tail here because of this 1/k singularity, so they can't be compared at small scales. The time zero signal here for the vortex patches is seen here. What you're seeing here at later times is the entropy cascade. There's a little bit of energy actually being carried to high wave numbers. Most of it's going to larger scales here. So in time, this is t equals 0, t 0.4, 4, and 40. There's a growth of energy towards large scales. The same thing is occurring a similar thing is occurring in the point vortices. There is an inverse cascade taking place, but too much energy ends up building up at large scales. So what you're seeing, the energy is too high for the largest scale. So you're forming some kind of large-scale pattern which you can't even see in the point vortex dynamics. So they're somewhat comparable, but there are significant differences found both at high and low wave numbers. All right, so I'm just about finished now. So the point vortex dynamics is focused on relaxation, seeking a typical random state for its energy. That seems to be what all the point vortex dynamics can do. The vortex patches, or any finite vorticity, has this ability, because it conserves entropy as well, for a dual cascade, and a significant portion of the entropy is irretrievably, irreversibly, to use your word before, lost at small scales. That irreversible cascade of entropy small scales has no analog for point vortices. It's trapped in the vortices. So the point vortices, once they start forming a little tendril, they break up into point vortices and they're there forever. They can't mix any further. And they just randomly bash around other vortices until they break everything up. And they create disorder. So the coherent structures in point vortices are short-lived. They fragment and grow disordered. And they do this by essentially seeking higher entropy. And the late-time evolution is utterly different from point vortex patches. So its conclusions then, the point vortex dynamics on sphere does appear to be ergodic, which is an important statement. nearly all initial conditions relax to a state which is statistically indistinguishable from the microcanonical ensemble mean. And there's a continuous variation of all statistical properties with the interaction energy or the inverse temperature. No, there's no surprises as you go from positive to negative temperatures. Dynamical self-organization does not occur. That's the main conclusion of all this talk. Merely relaxation. The microcanonical states are already organized, it turns out, at the largest possible scale. Think about the curves I showed earlier about the energy spectrum for the highest energy. Remember I said there was a surplus of energy at low wave numbers. Well, already for anybody doing classical two-dimensional turbulence, if they looked at that picture, they said, all the energy's at low wave numbers. You're not going to get an inverse cascade. They would there's no point. And yet the high energy regime that is supposed to be responsible for the formation of coherent structures is already super organized at large scales. It's already basically there. So there's no chance for dynamical evolution to those large scales. So the Onsager statement has nothing to do with the development of or the formation of coherent structures. It simply says something about possible end states of systems. And the evolution, finally, the evolution of dense clusters of point vortices may approximate the evolution of finite vortices only for a short time. And then point vortices cannot cascade entropy and therefore do not correctly cascade kinetic energy. Thank you.